In this podcast, we're going to talk about the combined gas law. The combined gas law expresses the relationship between pressure, volume, and temperature on a fixed amount of gas. The combined gas law is the one I prefer to use actually all the time. I like to use it in linear form, so I cross multiply the t's up so that everything is linear. So I have P1, V1, T2 equals P2, V2, T1. Okay, so I just like it all linear. The other reason I really like this equation is because you can get all the other gas laws that we've talked about so far from this equation. So if you were to cancel out the temperatures because it's constant and you were only given values for pressure and volume, you would have Boyle's law. If you were to cancel out the V's because the volume is constant and you just have pressure and temperature, then that gives you the gas law with the relationship between pressure and temperature. Okay, so you can use this equation to get all other equations by just scratching out the variable that is constant. As we're investigating all these gas laws, you can easily see that it's very hard to keep just two variables when you're talking about the gases. So it's really hard to keep one variable completely constant. So you see, like when we change the volume, it automatically changes the pressure and the temperature. When we modify the pressure, you see that the temperature changed and this little man had to push less on the wall, so there's a change in volume. If you were to increase the temperature, you would see that the temperature increases and the volume also is affected. So the volume and the pressure and the temperature are all very related. Therefore, it's easiest to talk about them all combined, like in the combined gas law. All right, here's an example problem. A deodorant can has a volume of 175 milliliters, so this would be our volume 1, and a pressure of 3.8 atmospheres, so that's our P1, at a temperature of 22 degrees Celsius, so that's T1. Now, temperatures we know can't be in degrees Celsius, so we'd have to add 273 to that. So 22 plus 273 will give us 295. So really our value of T1 is 295. And it wants to know what the pressure would be, so that's your P2. If the can was heated to 100 degrees Celsius, so this is our T2, but again, in the Celsius, you have to add 273 to get it to Kelvin. So that'd be 373 Kelvin. And expanded to 195 milliliters. This will be our V2. All right, so we have all of our variables. So now we're just going to plug in to the equation that we have. Oops. All right, so P1 was 3.8. V1's 175. Oh, snap. P1, V1, T2. Got T2. That's 373. Doesn't it look great? All right. Equals P2, which is what we don't know, times V2, which is 195, times T1, which is 295. Oops. All right. Now it's just the algebra problem. So we're going to multiply everything on this side, and we get 248045. And on this side we get P2 times 57525. Alright, now you want to get P2 by itself, so you're going to divide both sides by this 572. Man, dyslexia is getting me today. 57525, and divide this side by the 57. Doing it again. 525. Alright, so it cancels, so we get P2 is equal to 4.3 atmospheres. And that's all there is to it. So it's just like all the other ones. Same type of deal.